So the code is in GitHub, Yannet, PyTorch tutorials. I think it's also shared by Laura. So Laura. Okay, and I'm gonna start. So I have like two Python Jupyter notebooks. One is an intro to PyTorch. So PyTorch is a library for doing deep learning. And what I want to do today is to first introduce you to PyTorch, and then introduce you to how to do metrics factorization in PyTorch. Among other things, this is kind of the easiest example of how to do deep learning. So when I teach, this is kind of maybe my second or third example I give to people. So it's kind of a good way to introduce you to the world kind of deep learning. Okay, but again, we're here just for like a couple of hours, so this is gonna be incomplete. So ask me questions if something is not that clear. Okay. So yeah, so let me just start right here. So I am importing. I hope some of you know Python, and this looks kind of familiar. So I'm just importing a bunch of libraries here. And so what is PyTorch? So PyTorch has like 4 main kind of packages. One is like a library like NumPy. Hopefully you guys have heard about NumPy, but it's basically a library that does a lot of matrix operations, but on a GPU. And what means on a GPU is simpler, it's much faster. You can do a lot of more operations. Okay. The second thing is this package that does automatic differentiation. So Luis told you how we use gradient descent, which is basically a method in which you have an error function, and you differentiate the error function with respect to the parameters of your model, okay? And you do that to update the parameters, okay? What is super cool is that your model could be really, really complicated. PyTorch does automatic differentiation for you. And you're gonna see, it's a line of code. And that's very cool because you can have a very complicated model. You can just describe your model. It could be like really, really complicated. And then you do a line of code, you say loss.backwards, and basically PyTorch computes all the activity for you so that you can do a fitting of your model, okay? Does it make sense? So that's the second thing that it does. The third, it has a library for all types of, so deep learning models are based on layers and, functions and so on. So it has all of that already there for you to use. And lastly, it has a lot of optimization algorithms already implemented for you. So I started working with Keras, and I did some courses with TensorFlow, and after I fell in love with this. I really like it. It's very, you're gonna see, I'm gonna show you how everything is done in a simple example, but then you keep reading and you can understand very complicated stuff. So I love this a lot right now. And so it's a library that is kind of over a year old, I think. It's not even 2 years old. Right now is developed mostly at Facebook, and is basically eating a lot of TensorFlow, which is the older big library. Is eating a lot of users from TensorFlow right now because it's much easier to use. And more flexible as well. So anyway, so let me just introduce you to some of the key elements of PyTorch. So first, you can create random tensors. A tensor is just an array of multiple. In principle, you have kind of multidimensional array, let's say, right? So it could be a vector or a matrix, or it could be a cube if you want to think about it that way. So it has like multiple dimensions. And that is important because, for example, one image is a 3-dimensional array, right? And if you want to train a model on 100 images, you're going to have a 4-dimensional array, because one dimension is like the image itself. The other dimension is the fact that the image has like 3 channels, and then each of the 3 channels, right? So it's the 4-dimensional thing. People call it tensors, right? So you need that capability of having this kind of more dimensional matrices that just more than 2 dimensions. Okay, so PyTorch just handles that very easily. You have a function called view that is useful for reshaping. I think maybe a NumPy reshape function, something like that. Okay, let me show you an example of how you do this automatic. Yeah.
So in general, are you saying that if I have a GPU machine, I can just replace NumPy with PyTorch?
It's more than that. Yeah, it's that, but more than that, because PyTorch doesn't have automatic differentiation, for example. Okay, so yeah, so if you wanna get into neural networks and deep learning, you either use TensorFlow or PyTorch, or there are a couple of more other things out there, but these are the two major packages, and this is one of them. Yeah.
Let's say that aside from the deep learning capabilities of PyTorch, would it be feasible to use it as a NumPy replacement?
Yeah, sure, yeah, can. So for example, let me show you a basic idea of how automatic differentiation works. So you have this vector x, and I'm just basically having a list, and on top of that, I wrap this torch.tensor to create a tensor. But it has this particular thing called required grad equal true. Basically, this is saying, it's telling PyTorch that you can differentiate with respect to this particular vector. Okay, so I define that. I do .grad, and .grad at this point doesn't have really any. Actually, let me run this for a second, just in case I decide to run it later. Make sure that. Okay, never mind. So basically, so right now you put x.grad, it's supposed to be the gradient of that vector, but right now I haven't really done anything, so it's empty right now, it doesn't have anything. But then I can define this L. This L is a function of x. So basically saying multiply x by 2, add 1. When I add 1, because x is a vector, it's gonna add 1 to like every dimension of x, right? And then sum everything, okay? That will give me 48, okay? Now, basically, I do this, I do L dot backwards, and what this is doing is computing a gradient of L with respect to X, or anything that is a parameter inside L, okay? So after that, I can do X dot grad, and basically it's all 2. Why is all 2? Because 2, yeah, it's 2x plus 1, sum. So the derivative of with respect to x is just all 2, right? Okay, it's all good? Because you're gonna see that later. That's a magical line of code that is gonna compute, even if your model is very, very complicated. And right now I have this very, very simple model, which is like 2x plus 1 sum, right? And my model could be very, very complicated, and I do L dot backwards, and that by itself computes all the derivatives. Okay? Yeah. No, forward, I'll show you what a forward means, but that dot backwards basically compute the derivatives. There is a forward, you're gonna see later, yeah, as well. So then, okay, so then I just wanted to mention that, because I'm gonna use this later, so nn dot linear is just a function that will compute a linear transformation, yeah. Yes. And you know what I just did? I can do something like this. Dun, 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 2. And then I can, what is the out? How can I play this? I forgot. I always use the shift enter. Yeah, of course. Shift enter. So I do shift enter. Okay, shift enter. What are you doing here? Let's do it again. This is shift enter, shift enter, shift enter, shift enter, shift enter. Okay, do you like it? So this is, what is that vector there? Is 2x times x, right? That is 4 times x, right? If we know how to derivate. Yeah.
And, 4 variables? 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 4 variables
yeah, you can do anything here. You can, I'll show you later how this is gonna work. Okay, so basically, I told you that basically torch.nn have all of these layers. You know, layers are just transformations of variables. In this case, that one is a linear transformation. And you know, a linear transformation, let's think about the simplest linear transformation. Is like you have just basically a line, you know, 2x plus b, say like, you know, 5x plus 7, right? That is linear transformation. It's a line, right? So in this case, 5 times x plus 7 has 2 parameters, 5 and 7, right? From the point of view of the model, right? Suppose we are trying to find a model, a linear model. So we have a times x plus b. Our parameters are a and b, right? So y hat equal a x times plus b. So a and b are our parameters, are what we're trying to find, and this is a linear transformation, okay? So the way you define that in PyTorch is by this nn.linear, where d is the number of input features, right? And m is a number of output features. For example, neural network could be the number of input features, and then m could be the number of intermediate features or something like that. Okay, you're gonna see it in one example in particular very soon. So, and then I can basically do things like, well, what are the parameters of this linear map? You know, and then you see here all the parameters. So, you know, I don't want to get into all the details, but you're gonna see these are the biases, right? The plus b if I have like just one, and this is the matrix of that transformation. You know, this is basically the same as linear algebra, no? A, big A times x plus b, right? Big A is a matrix times your input has 5 features. You want 3 features out, okay? You remember your linear algebra a little bit? Okay, well, so these are my parameters here. So the first thing I want to tell you is how I can do linear regression in PyTorch. So and once you see kind of the idea, then I'm going to take you to a more complicated example of how we do matrix. Oh, that's great. That's what I was thinking. Maybe writing could be useful. Yeah, thank you so much. Okay, so you know, if you are trying to do a very simple model like linear regression, the first thing you do is that you create some fake data. Okay, you say, well, I'm going to you know, define A and B. My A is A, you know, my line. Let me actually kind of write this down. So yeah, let's do a crash course on linear algebra. It's like AX plus B, right? That's my model. So usually we call the model something like y hat, right? And right now, suppose that this x is just one dimensional, so it's a bunch of numbers. It's just one dimension. So basically, what I have here is that I have a bunch of points, and I would like to find the A and the B that fits that model the best, right? And how we're gonna do that, as Luis told us, right? So we have a lot of training data. So we have a lot of x and a lot of y's, right? And then we have this like y hat, and we're gonna do an error function, right? And which is the error function? The same one that basically, thank you. It's always a problem when they are not, okay. So what is the error function we have is basically the same one that that Luis was talking about. So we have endpoints, so we have a sum, right? Maybe we do an average, we don't care, it's the same. So, and we do like yi hat is basically your function on the xi. Okay, let me actually just write that down. Okay, and xi, comma yi are your points, training points, right? And what I call yi hat is basically A on the point xi plus b. Okay? Is that too much math, or is acceptable? Okay. So basically, what I'm going to show you is how we fit this. And the cool thing about PyTorch is that your training loop exactly shows you how we do it. What we do actually is we define this error function. PyTorch computes all the derivatives of this error for us, and then we use gradient descent. And gradient descent is just basically, we're going to update A and B at every iteration by subtracting a little bit of the gradient. Okay, and this is basically a method that, you know, kind of a most used method for doing minimization of a function. Okay, the other function, remember, is a function of A and B, because what we care about are the parameters. X and Y are actually fixed, is our data. Okay. Any questions on this? And I'm gonna just show you code that does this. Okay. And then gradient descent is a simple method, and there are other methods that are gradient descent like, that are more sophisticated. And I'm not gonna explain it to you, but I'm gonna use one of them instead of gradient descent. Okay. So, okay. So I think now I need to get rid of this for a second. Thank you. Yeah, so so the way you generate fake data is that you basically do the real model and you put some noise. And I'm not going to show you that much of that, but basically it looks like this. So there is an actual line underneath here, and I know my A and B, and I just want to get my A and B back. Okay. In this case, my A and B, I think A is going to be 3 and B is going to be 8, or the opposite. Yeah, something like that. So yeah, so what I want to do is to see if even that I'm putting a lot of noise in here, I can get the 8 and the 3 back from. Okay, that makes sense. Okay, so here I'm just defining. You know, this is like my error function. I don't know how much you are. You guys have seen vectorized code, but basically this thing here is the sum that you saw there. Okay, so I basically first square every element of y hat minus y, and then I sum. Okay, does that make sense? Actually, I put the mean, so it's the same. It's up to the constant somewhere. So I take the mean of everything. Okay. So for example, if I suppose that A and B are 10 and 5, then we can have an error. We can define an error, which is 3.39. Okay. So any questions?
So when you divide the error by n, that's what you use.
Exactly. Yeah.
So what about the difference between error and the mean of error?
It doesn't matter, because when you're minimizing a function, up to a constant is the same minimum. It's the same. It's going to be the same minimum at the end of the day. Yeah. So you're minimizing the same thing. It's just like a factor. Yeah. And usually people want to talk about the mean. I didn't write down here. I should have divided by 1 over n, which is the number of points. But it's the same. Yeah. Okay. So yeah. So first I'm going to show you kind of a non-PyTorch way of doing things, and then I'm going to show you the same code on PyTorch. Okay. So the first thing we do is that we wrap up everything. So I have this fake data. This is NumPy data. X and Y are NumPy arrays. And I wrap up everything into these tensors. Okay. I also wrap up A and B into some tensors. So I initialize them in a random way, and I wrap them up in some tensors, but I say required grad equal true. Why is that? Because A and B are my parameters, right? And I want to have derivatives with respect to A and respect to B. Okay. So these are the values of A and B. And then this is my loop. You know, this is basically a gradient descent loop. So what I'm doing here is that I have some, I'm computing a loss here. This is a function I defined before, which is that one, right? I'm computing, I have my x, my y, my a and b. A and b are initialized randomly, right? So I have a loss, okay? And what do? Loss backward. What does that do? Just compute a gradient of loss with respect to a and respect to b, right? And then what I do here, I say a.data. It's a bit complicated. So there is the data and the gradient. It's the two things that this PyTorch tensor have. Okay, so I'm changing the data using the gradient of a. Okay, yeah. Minus equal, that's subtracting. It's the same as a equal a minus something. Okay, it's the same as if I say a.data equal a.data minus learning rate times. Okay, you're subtracting from that value, that amount. Okay, yeah. So basically, what I'm doing is subtracting the learning rate times the gradient of a. Okay, and learning rate is basically because it's how fast you're gonna go into a particular direction. So usually it's like a kind of small number. It's actually a number that is the biggest possible that you can't, and it's complicated to figure out what's the right value. So you have to try different things basically. So that's the short version of it. And this grad equals 0 is basically something in PyTorch that has to be done because PyTorch has some very flexible. So basically, this backwards computes the derivatives but adds them to whatever is there already. So unless it's 0 out to begin with, it's adding to something else. So anyways, in PyTorch, you have to always 0 the gradients before you compute the backwards. Yeah.
How do you know how to pick the range for the learning rate?
That's a big question. It's a very big question, really. So let's talk about it over beer later or whatever. But it's a big question. It's like people are still trying to figure out the right research to do that. So, anyways, yeah. The question was like, how will I pick the learning rate? And that's a big question. I have some notebooks with some, there are some people who have done research on this, and they have some approximate methods on how to do it. And I can show you some stuff, but it's actually pretty complicated. Yeah, it could be completely complicated. So, okay, so, okay. So as you can see here, I go through this loop and I run it and I get some kind of small number. And if I look at what I get out of that loop, I get the 3 and almost the 8, right? So I get back the parameters that so a lot of in machine learning, when you have a method, it's a very good idea if you can generate the data in some way and try to recreate back the numbers you generated it with. Like this idea of doing this with basically if you have a model that you can generate and put some noise and try to get back the original parameters, that's the best way that you know your method actually works. So this is something that people use a lot. So generate your fake data first before, yeah. Is you don't have to. No, just like right now, it's very complicated. So like I have been doing deep learning for a couple of years now, and I haven't used a method in which this is useful. It's basically, PyTorch is very flexible, and you may be doing things in different models, and you have gradients in different places, and he's just aggregating those gradients. So unless you 0 out at the right point, he's just keeps aggregating stuff. And I'm going to show you how you do it, basically. But you have to remember doing it, otherwise you're kind of doing the wrong thing. Yeah. Yeah, if you go to Stack Overflow, people are like angry about this line of code. Yes. Yeah. So let me show you how to do this the same loop, but in PyTorch. Because right now I just kind of show it to you in kind of Python code more than PyTorch code. So the first thing I do is that I create a model, okay? There are two ways of creating a model. You remember that we talk about this linear transformation, right? So in our case, because our input has one dimension and our output has one dimension, okay? So my model just looks like this. You can create models with two different ways. One is using this NN sequential. Another way that you're gonna see that we're gonna use later is by, so if you use sequential, it's a very simple way of creating a model, but it's a very, very simple models that are a bunch of, it's a sequence of layers. So if your model is a sequence of layers, that's it, you use sequential. But sometimes your model is much more complicated. So you have to use something more like this, which is a class that inherits from NN module, has an init and a forward. And the init is basically where you define all of your layers and your parameters. You initialize everything, okay? And the forward is actually what are you doing with your X, okay? So basically, the forward has this X, which is your data, right? And what are you doing with that X? Well, you are applying this linear model that you define right here. Why you need to define this here is because you need to, the init, if you remember, the init is when you call that model the first time, the init gets called, okay? And the parameters get initialized, right? The forward is used when you call the model. So you first initialize the model, right? And then you call it a lot of times on different values. So that's what the forward is called, okay? So inside the forward, this is a very, very simple model, but you're gonna see all more complicated models, is what operations you do to get your output, okay? So let me tell you, this is, you get this, you're gonna get PyTorch today, okay? You're gonna get it, okay? So, and then you can also like see the parameters here. We have like 2 parameters. I create some more fake data here. There are a couple of things you have to know about PyTorch is that like the same as in NumPy, there are some operations that are kind of useful. There's something called unsqueeze. And what unsqueeze is doing is just changing the shape of your data. So, okay, so let me just kind of show you an example. So the original X was a vector that had dimension like 10,000. When you do unsqueeze, you get this kind of vector that has dimension 10,000 times 1. So it's just a different shape because basically certain functions like they want 2-dimensional matrices and not 1-dimensional matrices, basically. That's kind of why you have to kind of reshape a little bit your vector, okay? And this is handy, becomes handy many times. So basically, I can do y hat of my model in this x1, okay? And I get this. You remember, I have a model. The model is a linear model that's initialized with random parameters, okay? And I can say, well, given my x, can you give me y hat? Well, I can get you y hat, okay? This is how you do it. Another thing that is there is another part of PyTorch that is important is this idea of an optimizer. An optimizer could be gradient descent or stochastic gradient descent. This optimizer called Adam is a more sophisticated optimizer. It works pretty well in many ways. There's something called momentum. There are many different methods, right? And Adam is my default, and the default of many people. So you first have to decide the learning rate, and then you have to say, well, what are the parameters of your model, okay? And the good thing is that when you define a model in PyTorch, you can say, well, model.parameters, those are my parameters, okay? So what you're telling the optimizer is, what are your parameters and what is your learning rate? He has other things you can specify, but this is kind of the simplest thing you can specify. And let me show you my loop. You remember the loop before. This is exactly the same loop, but in PyTorch, okay? So the first thing I do is I say, well, give me compute y hat from the model, okay? So you just do it that way. Then you compute the loss, right? f.msc loss is a function in PyTorch. MSE is mean square error loss, right? So, and you give it y hat and y and squeeze. Y and squeeze because y hat and y need to have the same type of dimension, and that's it. You know, you have to reshape your data to look the way PyTorch likes it to look like. Okay. Then you do optimizer 0 grad. That's a line of code you should not forget about. It's annoying, but you just have to do it. And then you do loss backwards. And then you do optimizer step. What do you think optimizer step is doing? It's doing whatever you told them to do, gradient descent or Adam or whatever optimization step. It's just going a little bit of step in the direction of the gradient, maybe a little more complicated, but basically that's what it's doing, right? It's just updating a little bit the parameters of your model, okay, into the right direction. Yeah.
Look at what the current gradient is.
Yeah. So that's it. That's basically that's a loop for computing, and you're gonna see a very similar loop when I show you a more complicated model. But basically, this is a basic loop of PyTorch. Do you have any questions so far? So I obtained back my 3 and my 8, even a bit better. I am not gonna keep going on this, but I have logistic regression for you here. And I have also something that is important. There's something called the data loaders. It's very important in general. And I also have some 2-layer neural network right here. So you can look at the rest of it some other time. Any questions on this kind of basic PyTorch loop? Then you're ready for the big time. Okay, so they're gonna see. So okay, so let me show you some data. So there's something called movie length dataset. The data kind of looks like this. So there is a user ID, a movie ID, and a rating. There is also a timestamp that we're gonna ignore for the moment. So for example, the first line is user ID 1 with movie ID 31. Has a rating of 2.5, okay? So this data can be seen as a matrix, but in a way, seen as a matrix a waste, because in general, just 1% of that matrix actually has values. So a different way of representing the matrix is by this kind of a sparse representation, in which you actually just write the things that are non-zero, okay? Does it make sense? So when you have a matrix that is almost zero, nobody actually represents this as a matrix, but it represents this as this other way of like kind of more like sparse matrix, in which you just say, well, the value of user 1 and movie 31 is 2.5, okay? And then you specify all these tuples of users and movies and the value of the rating, okay? So it's the same data that Luis was talking about, but in a different representation, okay? All good? Good. So I am just putting this into a pandas data frame here. The next thing that is kind of a bit annoying is that I have to encode this data. The first thing I do is I take 20% of the data to be 80% to be training and 20% to be validation. This is not what people do in real industry, because you need to actually worry about the timestamp. So you actually, what you want to do in general is to say, well, I want to use, say, 1 month of data, the last month for validation, and the past data for training, okay? Here we're doing something that is not great, but we're doing that. So we're just kind of doing randomly. So what is going to happen is that you don't care that much how your method does in training. I mean, it has to fit training well, but you can overfit the training data. So what you care about is how your method is going to do on data that he has never seen before, okay? So that's what we're going to do. We have the training, and validation is because usually in machine learning, the validation set is helpful at finding also the hyperparameters of your model. So for example, how many features our users and items or movies are going to have, or how much regularization, something in general that is useful for overfitting, how much regularization we're going to do. So for all of that, you're going to use this validation set to help you find the right parameters for your model. Okay. So the first thing I have to do, I'm just going to, it's a little bit complicated here, but I'm just going to explain it to you. It's basically, I need all my users to be contiguous, and all the users ID to be from 0 to user ID maximum -1, and all the movie IDs from B to 0 to the number of unique users, okay? I need that because otherwise it's wasteful. So I have to encode the data to do that. And then I have to throw away anything, the validation, that is not in my training. So if I don't have a user per item pair in my training, I'll throw it away in my validation, because this model cannot handle things that doesn't exist in the training, okay? Just because of that. This particular model cannot handle new users and new movies, okay? So that's basically what this part is doing here. And for example, I have this little matrix here that I will have like user ID 11, movie ID 1. So that will go to user ID 0, movie ID 0, okay? So basically that's what I'm doing, okay? So I encode my training and validation. And let me tell you what is an embedding layer. An embedding layer is basically a layer that is going to assign random representations to users and items. You remember how Luis was talking about, you know, giving like 0.5 to comedy and 0.7 to action, right? Here we're going to have a specified number of factors or features, right? Number of embedding features, and then we're going to get a matrix that for each user and each movie, I am going to have a vector of random numbers. Okay, that is an embedding layer. And then what you do is that every time you want to look into user 1, you're going to look up that particular feature, like this row for your user, and you want, you know, movie 31. You look up movie 31 from that, and you update those particular parameters, okay? So your parameters are these embedding matrices that I have here, okay? So I'm gonna show you an example on how this works. So for example, suppose I have 10 users, and I'm gonna have an embedding size of 3, okay? So I create my matrix by doing this, okay? And then in practice, what I want to do is look up. So I have this A is my vector of, say, users, right? So my user 1, user 2, then I want user 0, user 4, user 5, and then I want user 1 again, okay? So I can do embed on A. So what I want you to pay attention to is that the first row is equal to the last row, because this is a representation of user 1, right? So you can look up that row every time you want, okay? And it's going to give you the same value for the same user, okay? So basically, it's just a matrix that you tell them how many users you have, how many, what is the, how many features you want, and it gives you a random matrix to begin with. And then our model is going to update that matrix, because those are the parameters, okay? So let me tell you about the most basic model that Luis talked to you about. You remember that in the basic model, what we were doing is a dot product, okay? So, what's in here? So what I have is, for example, UI, which is basically UI1, UI2, UI K, so this is a vector for user I, right? And I have Vj, which is Vj1, Vj2, Vjk, and this K is the same K, okay? It's the number of features I decide to use, right? And then my model, Yij hat, so the rating for user I, rating movie J is just ui.vj. This is a dot product, so it's just basically ui1 times vj1 plus ui2 times vj2 and so on, right? Okay, so how is this similar to, do you actually see that this is exactly the same as what Luis was talking about, right? So we have this big matrix I and j, except that most of it is empty, right? And then our model is just a very simple dot product, okay? And what are our parameters? How many parameters do we have here? So we have, suppose that we have big N users maybe, and big M movies. How many parameters do we have? What about K times N, K times M plus, right? Because we have a matrix of K times N. This is the amount of parameters for users. K times M is the amount of parameters for movies. And then we sum them. That's all the parameters we have for this model, okay? I'm gonna show you more models, but this is kind of the more basic one. This is a good. So then let me show you this model in PyTorch here. So, so in my init, I have to specify how many users do I have, how many items or movies I have, and what is the embedding size. Embedding size is basically what is the number of, how big is my representation of that user and that item, okay? And for now, let's say it's 100, okay? So then in here, I basically initialize everything of my model. So I am calling this n embeddings, right? On the number of users and the embedding size, on the number of items and embedding size. And then this particular model is kind of funky about initialization. So it works well if you initialize with like small positive numbers. And we can talk about why is that and so on, but let's just, for now, NN embedding will initialize in some way, but in this particular model actually works well if you initialize it small positive numbers. So let's try to do that. So I could potentially not do this, and it would also work, but maybe it will converge slower. So I'm basically kind of forcing a little bit. Okay, does it make sense? So basically here I'm just initializing this weight matrix with like a small uniform positive number. Well, a bunch of numbers, right? And then what is the forward doing? So the forward is taking U is a list of users, and V is gonna be a list of movies, okay? The first thing it does is looking up the vector for every one of the users. You remember I showed you how to look up, you just basically, I showed it to you before. I am gonna show you another example of this. And V is just looking up the vector of all of these movies, okay? And then I'm gonna show you why the expression looks like this, exactly in a minute, okay? Let me show you actually why this is doing. So here is my little matrix that I showed you before. I have like user ID 0, movie ID 0, rating 4, user ID 0, movie ID 1, rating 5, and so on. So in here I have 7 users, 4 items, and an embedding size of 3, okay? So I'm basically here just initializing these two matrices, and these are the users. So if I print U, it's gonna be just the list of users, 0, 0, 1, 1, 2, 2, 3, 3, and so on, okay? So the first thing I do is that I look up the embedding of users, this U. Let me show you what U looks like. So the first two vectors are the same. Why is that? Because they're the vectors of the 0, right? The two zeros, and then there are 2 1s, and then 2 2s, and then 2 3s, and then 2 4s, and then 5, and then 2 6, right? So basically, I'm looking up all of these vectors, okay, of U and V. Then what I'm gonna do is I'm gonna do an element-wise multiplication of those vectors, okay? Because what is a dot product? If you have two matrices, so you first can do an element-wise multiplication, and then you do a sum over the rows, okay? And that will give you dot products of all of these vectors. Okay. So basically, that's what this is doing. So you first have your elements, 0, 0, 1, 1, 2, 2, and so on. Look up the matrix, then do element-wise multiplication, and then you do a sum per row.
That has non-zero values?
Yeah, is that, you know, what you start with is this matrix, you know? You start with the actual ID of the users, and the first thing you have to do is to look up their representation, their embedding, okay?
Are you saying that you're getting the value?
Yeah. Yeah. So I'm looking up all of these embeddings, okay, of the users and the items. I am doing this element-wise multiplication, and then I have to do this sum, and that's basically equivalent to doing a dot product per row. Okay. This is a little bit different than what Luis showed you, but this is more efficient because you actually never want to do a real matrix multiplication the way he did it, because that will take way too much space. There are a bunch of values that are empty, and you don't want to compute those because you are not doing error on those values. You're just doing errors on the non-empty values. I don't know if that makes sense. Yeah.
My question. So if you have the user has not rated any of these movies, you still have, you want to have a dense and not sparse.
Yeah, and that's not the case in this application. That's the main thing we're doing. This is a method of dimensionality reduction in a way. So basically, this is a dimensionality reduction method. There are many ways of doing matrix, but partially what we are doing is that the original, this huge matrix is empty. It's mostly empty. So you need to find like a more compact representation. Your model is more compact. You know? Most of these matrices are just like 1% or 0.5% occupied. Like the actual matrix is real empty. You know, think about how many movies you have ever rated. You know, or even how many movies you have ever seen from all the possible movies, right? So does it make sense, this model? Like, do you believe me a little bit? A little bit, just like you can. So, but again, this is a different multiplication in a way. It's not a matrix multiplication because we don't want to generate the non-empty. We just want to generate on the training set, basically, on the movies and on the tuples that we actually have data on. Okay.
Does it have any relationship or similarity to what embedding?
Yeah, it has. It has. It is very actually the word embedding. One of the methods is just this. It's just this with a few other things. Yeah, it's very. You can see it as very, very similar. It's just basically there are different ways of training those embeddings, and there are different ways of training these embeddings as well. This is just the most basic model. Okay.
I have a question about it. Return like sum of one. If you eliminate that one, just sum of the empty parentheses, would that work?
No, because of what I just showed you here. Here, let me show you again. So basically, when you just do the dot product, this dot product here, this is an element-wise multiplication. So what you get is a matrix. And what I want is a number. I want a rating per user and movie pair. Okay? So I want a number, not a matrix. I want actually a list of numbers, one per each one of the tuples, right? So no, it doesn't. Yeah.
What I guess this question was on sum one. Yeah, the number one.
Okay. There is a probably default, but I'm summing by rows. If you put 0, it's gonna sum by.
If you put nothing,
that's the access. I am not sure what is the default. If the default is 1, it's gonna work. If the default is not 1, it's not gonna work. Exactly. Yeah. So I don't know what is the default. Maybe it's gonna most likely it's gonna give you an error. It's gonna tell you, well, tell me which dimension you want to sum. Or maybe it's gonna sum the whole thing actually, and you don't want that either. So that is an important. Yeah, so you can try, but I don't think it's gonna work by default. Yeah. So let me show you how you train this model. Okay. So the first thing you say is like, well, how many users you have, how many items, and this is how you define your model. Basically, you just call the model you had before, and you say, well, this is the number of users I want, the number of items, the number of embedding size. So here you are initializing your model. You're getting random, you're initializing randomly all of your parameters. Okay. And if you had a GPU, you can put .CUDA here, and that will put this model in the GPU. Okay. It turns out that this runs very easily on my computer, so it should run yours very easily too. Yeah. That's it. Yeah. Yeah, that's it. Yeah. And then you have to put CUDA here too, but that's it. Yeah. But you have to run it on a GPU. Yeah. So basically, let me show you the training loop. The training loop is very similar to what you saw before, but now we have a more complicated model, but it's the same. You're gonna see it's the same. So we have an optimizer. The optimizer, do you agree, is the same? There is something called weight decay, and this is a regularization parameter. But in principle, do you agree it's the same? We just said, hey, give me the parameters of my model. Well, they're more complicated, but you have them, right? This is this is kind of something that you have to do that I didn't tell you before. It turns out that you have to use model.train when you're training and model.eval when you're evaluating. And it has to do with, I don't want to get into why, but you kind of have to do it. There are a few things that work differently when you're training and when you're evaluating. One of them is dropout. I don't know if you have heard that. So it works kind of differently when you are training or evaluating. And then what I do is that I go through a number of epochs. Epochs is basically running over your data multiple times. I take all my users from my data frame. I tell all my items from my data frame and all my ratings, okay? I have different models here, and some of the models I need to unsqueeze the ratings, and in other models I don't have to, and that's just because the models are a bit different. Then I do this, I give users and items to my model, and I get y hat, right? I compute my loss, which is the same loss as I used before, MSE loss, between y hat and my ratings, my actual ratings, right? I do optimizer zero grad, as I told you before, you have to do. I do loss dot backwards. I do optimizer step, and that's it. I print my loss, and at the end of here, I also try to compute the model in the test loss. And there's a function that I have right now, right here, which is just the same thing, but it's in evaluation mode, and it's working with the validation set instead of the training set. Okay, so it's just to understand how good are you doing on your validation, which is what you really care about, right? And this is basically doing the same thing, except that it's not training, it's just printing the loss function. Okay, so any Any questions so far? So that training loop, that's as complicated as you get for a while until you're doing something a little more crazy. The training loop is the same for all these models. The good thing is that you can see it because when it gets more crazy, you also get to see it and understand all the details of it and to change it. So that's also what makes PyTorch very flexible. Okay, so what time is it? I can stop here or keep going. I don't know. What time is it? 8:20? How much time I have?
You have 2 minutes.
Okay, let me just give you. I will gonna quick glance of a couple of more models and then I'll be done. So and then what I do here is basically I change the learning rate a little bit. I start with a higher learning rate and go lower and get to this number that is pretty decent if you look at this data set. You can have a different model. For example, this other model is very similar, but it has a bias. So it's like saying, well, maybe some users rate higher, and then you have a bias for each user. And maybe some movies are better or worse, so there is a bias for each movie. So and that just means a slightly different formula and more parameters. And hopefully you get a better model because it fits better because you have a bias for each user and a bias for each movie. Okay? It's just more parameters. So my model is very simple. It's a dot product of users and items. So instead of having that you have that plus a bias for the movie and a number for a movie and a number for a user. And it basically, I'm just giving you this idea that it accounts for the fact that maybe a particular user just likes to rate higher or lower, or a particular movie is just more popular in general, So you just have to sum just this thing that has to do just with the user or just with the movie. It's just a more complicated model. It's just that. Yeah, exactly, and that would be the same. Yeah.
Essentially, just controls.
It's more it's a different model. It's more parameters. Yeah, it's basically like saying when you have a linear model that you have a times x plus b. It's basically saying put in a b. B could be 0 or it could be another parameter. This is what it's called a bias, right? Here you have two biases. This is called kind of a bilinear model or something, that model. And this is just basically saying, oh, let me add some biases that can be learned, right? It's just going to fit your data a bit better, hopefully.
You're adding one bias per user and one bias per movie.
Per movie, yeah.
So
Yeah.
plus
Exactly. Yeah. And this is just basically the code that does that. It's very similar, So let me show you a more interesting code that. So basically, nobody tells you that this model is what you need to have. So instead of having this, let's just think about this other thing. Now I'm telling you, well, I just want to make my model a more complicated function of this UI, VJ, and potentially I can add here anything you want, like tags about that thing, or timestamp, or the weather, or whatever you like. So because this function is more complicated and you're not doing, say again? Exactly, any tags, anything, because this is a more complicated function. I don't have a dot product anymore. Then I can basically, this can be more flexible and I can add anything I want about other, you can do feature engineering on the text and, add whatever, other stuff. Whatever other things you want about that, okay? Actually, what YouTube, the recent, paper that they wrote, it's not that recent, but it's kind of recent. What they do is that they compute UI and VJ from one model. And then in real time, they store this UI and VJ, and they use another model, a faster model, for real time. Okay, so it doesn't even have to be one model. It could be that you compute one model and then it computes the representation, the embeddings of that user and that item. And then in real time, you use another model for, what was the movie that she just saw, So you use basically, for example, maybe this model is too complicated and it needs training for a couple of days or a few hours or whatever. So you have a kind of overnight model, and then you have another model that is more of like, hey, she just saw X, Y, and Z, and it's not about what you want, it's also about what are you up to right now, And maybe that model is a cheaper model, say regression or something, and you're using this and that, but you're not training on them, you're just kind of using them. And you have you're kind of and this happens a lot, like these two-stage models, and that's kind of what they were using at some point when they wrote this paper a few years ago. Kind of transfer learning. I mean, it's not the same data, but I think they do it for different purposes. It's just that they need something fast, and that faster model has to train faster as well. So they have something more kind of like long-term, whatever, and then you have something more like what they kind of use. And I don't know if this is what they do now, but this is what they wrote on that paper. So anyway, so they had this kind of much more complicated.
Yeah, for example, let's say you want to train on the date, right? That's too expensive. User and also the date. But to serve on the date works. Because, for example, we can say if it's Christmas, more like serve on Christmas. So like you can put a much more expensive function here for serving, but for training it would be like.
Yeah. So basically, what I'm going to show you here is that this F can be a neural network. So, and then you will have two types of parameters: the parameters of your embedding and the parameters of the neural network. Okay, and then now, even for example, the size of the embedding for the user could be different than the size of the embedding for the item, because I don't care anymore. They could be different vectors. I don't have to multiply them anymore. They can be more complex. Maybe users are not that complicated, so you use 100, and then maybe movies are more sophisticated and you use a bigger size for that embedding. So you don't need to now have the same size for the other embeddings. So anyway, so I am actually not even going to get into this model because I think we don't have time. But what this is doing is just implementing a slightly more complicated model in which it's just more general, and that you can potentially add anything you want in here. A lot of more features about the users and the movies in here. So I think I'm going to stay here, and then you guys can ask me now questions or later. No? Any questions now?
This complex function beyond the
Yeah. So that last model that you see here, right there, is a small neural network that basically does that. So the thing to keep in mind is that now you have the parameters of the function and the parameters of the embedding. So you have many more parameters, and that is slower, and We
have this tiny underline.
You mean?
When you're loading in.
The data is also like at the beginning of the notebook, I tell you how to get the data as well. Is that the So I split training and testing at some point. So I don't know if you saw that, but the data is ratings.csv. And for example, in that, you can also have info about the movies and all of that, all other info that I'm not using. You can potentially use the kind of the bigger model. Okay. So any more questions? The other kind of topic that is kind of very interesting is implicit ratings. Implicit ratings is the ratings that you don't have 0, 1 to 5, but you just have like somebody watch a movie or didn't watch it. And the way usually people do that, or one way to do it, is that whatever people watch, you call it a 1. And whatever people don't watch, you call it a 0, but these are too many zeros. So what you do is that you sample the zeros. So if you train a model, what you say is like, well, I'm gonna take everything that Louis watched, okay? And then I'm gonna sample what he didn't watch randomly, and you call that zeros, okay? And now you can train a model with like that, just with 0 ones, basically.
Another question. I think there's a potential problem that I watched movie Hawaii with my son. So
Yeah, it's very complicated, you know, and they have much complicated, but I'm just telling you the basic idea. The basic idea is that you cannot do anything with just zeros, with just ones, so you need some zeros. And the way people do it is called negative sampling, is that you sample from the things that the user hasn't seen. There are many other complications, you know, like those that you're talking about, and you know, people have ways to, they have ways to figure that out, but it's a very complex system, right? And none of us have actually worked at Netflix. So, yeah. So they may have many different signals, and they probably make models from those signals, and they put them together as even bigger models, I guess.
Netflix went to like and just like from 1 to 5.
Exactly.
What was the
Because people don't do it, you know, people don't rate, you know, people don't, so you just want more data, so you have to simplify it for the user, you know. Otherwise you don't get the data. Yeah. Okay, thank you so much. I'm here for any questions.